All right, we're going to look at a concept that's very important in lots of different areas of mathematics, especially algebra. It can be used to help you solve inequalities, to graph, to find the domain of a function, lots of different applications. But what we're going to do is see how to determine values that make a polynomial 0, positive, and negative. All right, so we will start with an example. And I'm going to refer to this process as building a number line sign chart. So I might call it a number line chart. I might call it a sign chart. It's all the same. It's a very visual representation here. So let's say create the number line sign chart. Create the number line sign chart. And let's say that our function is y equals x plus 2 times x minus 3 squared times x plus 5 cubed. Okay, so this is our function. It's a polynomial and it's already factored, which is very nice. So what we have to do here is if we want to know where this polynomial is 0, we have to find the zeros. We could also call those critical values. Now those are easy to find here because it's factored. So the zeros are the x values that make the whole thing equal 0, which when it's factored are also the values that make each factor equal 0. So clearly our zeros or critical values are -2, +3, -5. Those are the x values that make the whole thing 0. So what we're going to start with is we're going to create a number line of x values, and we're going to cut the number line apart at the critical values and make sure we put them in order. So the first critical value is -5, and then we have -2, and then we have +3. Okay. Now, what we want to do next is above the x number line, we want to track the outputs of the function, the y values, okay? And we're only interested here in y values as far as being 0, positive, or negative. We don't need specific y values. So 0 is the only particular y value. That occurs at the critical values here. So we know that the output at each of those x values is 0. And so what I'm doing here is I'm tracking y values above my x number line. Okay? So I know that these three x values make the whole function equal 0. So my y values are 0. Now, as far as the regions in between, I don't care what the particular y values are. I just care whether they're positive or negative. And polynomials have this fantastic feature. They are smooth, continuous graphs. Okay, so if y is 0 here, then that means every y value in this region has to be negative or positive. Okay, and they're all the same. So what we're going to do is we're going to kind of track the y values by setting up this structure, right? So the y values here are calculated as x plus 2 times x minus 3 squared times x plus 5 cubed. And we're going to set up that structure in each of these intervals. And this is kind of the slow way to do this, but I want to make sure you understand what we're doing. And then we'll come back and we'll do this exact example quicker, and then we'll do several other examples as well. All right, so we've got, let me kind of put a box around the zeros so we can easily see where each region is separated. Okay, so now what I want to do is let's just analyze the x plus 2 factor. Okay, the critical value for x plus 2 is -2. And if you plug in numbers to the left of -2 for x plus 2 is negative. So I know that to the left of -2, the sign of my x plus 2 factor, that first factor, is negative. And then when I cross over -2, right, if I plug in numbers bigger than -2, that changes to a positive. Okay? So that's just the x plus 2 factor, and the only place it changed sign was at its critical value of -2. Now let's track the x minus 3 factor. Okay? If I track the x minus 3 factor, I know that its critical value is 3. And to the left of 3, x minus 3 is negative. So negative, 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 that's everything to the left of 3. And everything to the right of 3, well, that's going to give us a positive when we plug in numbers bigger than 3 for x in the x minus 3 factor. We'll take into account the powers in a moment. All right, let's look at x plus 5. The critical value is negative 5. If I plug in numbers to the left, it's negative. If I plug in numbers to the right, it's positive. Okay. So now we have to go through and determine if this product, this multiplication, yields a positive number or a negative number, and do that for all the intervals. So here's the idea. We have a negative times a negative squared. Well, a negative squared is positive, right? So we've got a negative times a positive. That's a negative. A negative cubed is a negative. So we've got a negative times a negative. So in this region, y is positive. Okay? Because we've got a negative times a positive times a negative. In the next region, we've got a negative times a positive times a positive. Well, that's a negative answer. Then we have a positive times a positive times a positive. That's a positive answer. Okay? And then we have a positive times a positive times a positive, which is also a positive answer. So what we see is whenever x equals negative 5, y is 0. But whenever x is less than negative 5, y is positive. Whenever x is between negative 5 and negative 2, y is negative. When x is between negative 2 and 3, y is positive. And whenever x is bigger than 3, y is positive. And this is useful, again, for lots of different applications. So right now, we're just practicing building this number line chart. Now, the cool thing is this whole thing can be sped up. All right? So let's run through this example one more time and see how this can be sped up. And I'll kind of give you some foreshadowing of it. So you notice that the negative squared was the same sign all the way through, right? Or the squared factor always gave us a positive output, whether we had a negative in it or we had a positive in it. Now, so remember, that came from the factor of x minus 3, which had a critical value of 3. So that's where it changed from a negative to a positive. But because it was squared, the total output, you see, did not change here. It was positive, the whole thing was positive before and it was positive after. And the key to that is because of the even exponent. Okay? So this 3 has an even multiplicity, a squared exponent. It's an even multiplicity. So what you see is the sign of your y value does not change when you cross over a 0 that has an even multiplicity. Okay? And the sign does change, so let's look at negative 5. Negative 5 had an odd multiplicity of 3, and you can see that the sign of the y value did change. All right? So that's what we're going to utilize to help us do this problem again in a much faster way. This totally works. Hopefully it makes perfect sense. It's really clear what's going on here to get these signs. It's just kind of slow. Okay? So let's look at a faster way to do this, using those multiplicities now. All right, so let's set up our number line chart again. We've got negative 5, we've got negative 2, and we've got 3. We're going to utilize multiplicities now, so let's go ahead and write those in. Negative 5 has a multiplicity of 3, so that's an odd multiplicity. Negative 2 has a multiplicity of 1, so that's an odd multiplicity. And 3 has a multiplicity of 2, which is an even multiplicity. So these are the x values. And now we want the y values. And we already know that these are the zeros. These critical values are zeros. So the y values at each of those is 0. Now, what we need are signs between the 0 outputs. And the way to get us started is with end behavior. Okay? End behavior is going to tell us what happens with the signs on the ends of our number line chart. So if I look at this and I want the end behavior, I would need the leading term. And because it's factored, I'd have to kind of multiply it all out to get my leading term. So if I take this, the leading term here, that's x, and that's multiplied by x squared, and that's multiplied by x cubed, we can see that when we multiply all of that together, we get x to the 6th as our leading term. So our end behavior does this, which means that on the ends of our graph, our y values are above the x-axis. We have positive y values. So I know that the signs on the ends of my number line chart are positive to match the end behavior of the graph. So we're kind of using what we know about end behavior to help us with this number line chart. Okay. Now what we can do is use our multiplicities, right? We can use our multiplicities. Since this is an odd multiplicity, I know that those two signs, the y values here, change. They're different, okay? And since this is an odd multiplicity, I know that whatever sign here is different than whatever sign is on the other side. And because this is an even multiplicity, I know that these signs have to be the same. Okay, so let's kind of track that through now. So here, I had a positive with an odd multiplicity, so the signs have to be different. That means this sign has to be a negative, has to be different than the sign before. And then this multiplicity is odd, meaning this sign and this sign have to be different, so that's a minus, that has to be a plus. And then you can just check at the end, since this multiplicity is even, these two signs have to be the same, and they are both positive. If you ever get to a point where you run into a contradiction, you made a mistake somewhere. You missed a 0, you got a multiplicity wrong, or something, okay? So there's our number line chart. We didn't actually have to plug any numbers in to do it. We used end behavior to get the signs on the ends, and then multiplicities to get the signs in the middle. Let's try some others here. I've got, looks like 2 more examples. We'll use the same instructions, create the number line sign chart, and I'll give you a new function. So now let's look at y equals, or it could be f of x equals negative 2x squared times x minus 4 to the 5th power times x plus 6 to the 4th power, okay? So now, again, really nice because it's already factored, which makes it easy to identify zeros and multiplicities. So that's where we'll start. We'll plot out our zeros and multiplicities on our number line, on our x number line. So we've got negative 6, positive 4, and 0. So negative 6 is first, 0, and then 4. Negative 6 has an even multiplicity of 4. An even multiplicity. 0 has a multiplicity of 2, so that's also an even multiplicity. And 4 has a multiplicity of 5, which is odd, okay? Now, let's track our y values. And I know that because this is a polynomial and these are my zeros, I know the y values here are 0, okay? Now I need the signs in between, so it'd be nice to get the ends first, the end behaviors, and then I can use my multiplicities to fill in the middle. So my leading term, because this is factored, I have to multiply it all together to get my leading term. So I've got negative 2x squared times x to the 5th times x to the 4th. And when I multiply all that together, I get negative 2x to the 11th. So it's an x to the 11th leading term, but multiplied by a negative, so it's flipped over. So x to the 11th is x to an odd, typically goes down and then up. So it's going to flip over and go up and then down, okay? That means that my left sign on my sign chart, my y value, since this end, the left end is above the x-axis, my y value is positive. And over here, we're below the x-axis, so the y values in this region are negative. We have an even multiplicity, so the sign stays the same when we cross that 0. Even multiplicity, so the sign stays the same. Odd multiplicity, so the sign changes and everything works. It all matches. And that's all there is to it. You see how simple that is. Now, something we've been working with are factored polynomials. So let's see what we do if we don't have a factored polynomial. Same instructions. All right, so last one, instead of using y, let's use f of x. F of x equals x cubed minus 2x squared minus 4x plus 8. And so when we have a polynomial that's not factored, it makes it harder to find the zeros and their multiplicities. But it does help us identify the leading term because we don't have anything to multiply together. We know the leading term is x cubed. So we're going to go ahead and look at our end behavior, which is like this. So when it's not factored, leading term and end behavior are easy to identify. But zeros and multiplicities are harder because you have to now factor the polynomial. So let's run through the process of factoring this guy. There's 4 terms, so I will use grouping. Out of the first 2, I'll pull an x squared, leaving behind an x minus 2. And out of the second group, I've got a negative 4, so I'll pull that out, also leaving behind an x minus 2. And then looking at my 2 groups, they have an x minus 2 in common, so I'll pull that x minus 2 out, which leaves behind x squared minus 4. X squared minus 4 is a difference of squares, so we have to continue factoring. So we've got x minus 2 times x plus 2 times x minus 2. And because we know multiplicities are going to be useful for us, let's rewrite this as x minus 2 squared times x plus 2. So that's our factored function. And now we know the zeros are positive 2 and negative 2. Negative 2, of course, comes first, then positive 2. Negative 2 has a multiplicity of 1, so that's an odd multiplicity. And positive 2 is our 0 here, has a multiplicity of 2, which is even. Then we've got, well, the y values at both of those are 0, right, because they're the zeros of the polynomial. The end behavior tells us the left end is below the x-axis, so we have negative y values. The right end is above the x-axis, we have positive y values. Then we use our multiplicities. Odd multiplicity tells us the signs on either side are opposites or different. So since this is a minus, this has to be a plus. Even multiplicity tells us that the sign on each side has to be the same. They are, we're all good. Okay, again, so that's number line charts for polynomials, assuming that they're factored or that we can factor them and find the leading term in the end behavior. In my experience, what most students miss are this leading term. They forget to even look at it and they kind of guess, and then their signs don't match up and they get all confused. So make sure you get your leading term and end behavior right, because that's the starting point for all of these signs, all right?